Have you ever driven over a massive bridge and wondered, how does this thing actually stay up? Well, the answer lies in technology that can see movements so incredibly small, they're completely invisible to the naked eye.
So let's start with a really important question. Every day we trust our lives to these giant structures, right? But how do engineers really know that they're safe?
Well, the secret is a field called structural health monitoring. And it's all about detecting these microscopic vibrations and shifts in a structure to catch a tiny problem long before it ever becomes a big disaster.
Now, to really get what we're talking about today, we've got to take a quick trip back in time. Yeah, back to high school physics. Because there's one simple concept in there that is the key to unlocking this entire thing.
Okay, first up, speed. Pretty simple, we all know this one. It's just a number. It tells you how fast you're going based on the total path you traveled. You drive 60 miles an hour, your average speed is 60 miles per hour. Easy enough.
But then there's velocity. And it seems kind of similar, but here's the catch. It's a vector. And that means it has two parts, how fast you're going and in what direction. So not just 60 miles per hour, but 60 miles per hour north. And this is crucial. It's calculated using something called displacement, not distance.
So this is the whole game, right here. The difference between distance and displacement. Distance is the total journey you took, every single twist and turn. But displacement, that's just the shortest, straight line path from where you started to where you ended.
All right, let's make this crystal clear. Picture a race car on a 1-mile track. It does one perfect lap. The distance it traveled is, obviously, 1 mile.
But hang on, where did the car end up? It finished right back at the starting line. So the straight line distance from its start point to its end point, its displacement is zero, nothing.
And this leads to a pretty wild conclusion. Since velocity is based on displacement, the car's average velocity for that entire lap is 0 miles per hour. Kind of messes with your head, right? It was moving the whole time, but its velocity was 0. Keep that idea in your back pocket, because it's about to become super important.
Okay, so why the physics lesson? Because that little distinction is exactly what was causing a massive problem in structural monitoring, a little gremlin called drift, where the old ways of measuring would literally get lost over time. You see, for a long time, engineers used systems like the KLT tracker, and what it does is it watches a video and it calculates the velocity of a point as it moves from one single frame to the very next. It's a step-by-step, frame-to-frame measurement.
Now, you don't have to take my word for it. Here's a quote from the actual research paper that solved this. The old method had to add up or integrate all those thousands of tiny velocity measurements. But here's the thing. Every single measurement has a tiny, tiny error. And when you add thousands of tiny errors together, they accumulate into one big error. That's drift.
The best way to think about it is like a car's GPS that's just a tiny bit off. After a few minutes, it's no big deal. But on a long road trip, that tiny error keeps adding up. And by the time you get to your destination, it thinks you're miles away from where you actually are. Your position has drifted from reality.
So yeah, this drift was a huge headache, but a team of engineers came up with an absolutely brilliant solution, and they did it by going all the way back to that basic physics lesson and just thinking about the problem differently. They switched from velocity to displacement.
And here it is, the aha moment. Instead of measuring from frame 1 to frame 2, and then 2 to 3, and 3 to 4, and so on, the new deep flow method does something so much smarter. For any given frame, let's say it's frame number 5000, it measures the movement all the way back to frame 1. It directly measures the total displacement from the very beginning. And by doing that, the errors simply can't add up. No more drift.
But wait, there's more. The old way needed to find a really obvious feature point to lock onto, like the corner of a window or a bolt head. But what if you're looking at a smooth, plain concrete wall? It had nothing to grab. This new method, though, can create a dense mask of tracking points on pretty much any surface. That makes it way more flexible.
Okay, so the theory sounds incredible, right? A system that doesn't drift and can track anything. It sounds like a game changer. But does it actually work in the real world? Well, they put it to the test.
The lab setup was actually pretty simple, but really clever. They took a steel beam, made it vibrate, and just filmed it with a normal smartphone. Then they processed that video with both the old KLT method and their new deep flow method. And they compared both of those results to what a super-duper accurate laser sensor said was the truth.
All right, let's look at the hard data. Now, RMSE, or root mean squared error, sounds complicated, but all it means is how wrong was the measurement. And for this, a lower number is way, way better.
You can see it immediately. The proposed method's error is just tiny compared to the old KLT tracker.
And if that table wasn't clear, this bar chart just screams the results at you. Look at that. The error from the old method is almost 4 times higher than the new one. I mean, this isn't just a small improvement, it's a giant leap in accuracy.
Let me put it another way. At its worst, the old KLT method was off by nearly 20%. A 20% error. When you're talking about the safety and integrity of a bridge, that's a frankly terrifying level of inaccuracy.
And the new deep flow method? Its maximum error was less than half of 1%. It's absolutely fantastic. An incredible improvement in precision, and it's all done with a camera you have in your pocket. So what's the bottom line here? It's that by simply going back to a basic high school physics idea, the difference between distance and displacement, these engineers created a tool that's cheaper, works on more surfaces, and is just massively more accurate. It's such an elegant solution to a tricky problem.
And that really just leaves us with one last question to chew on. In a world that is always getting more and more complicated, this incredible breakthrough came from going back to the absolute basics. It just makes you wonder, what other huge, complex problems are out there just waiting for someone to find the simple answer that's hiding in plain sight?